This one is 3.16. Here we have a possible set of muscle forces given on this femur bone, which are this force P right here, this one here, this one here, and this one right there. We need to find out the reactions at these support points, which is RA here and RD at this point. We also need to find out the transverse forces and bending moment along the length of the shaft of the bone. We also have to comment on the compensating effect of the muscle on the reduction in bending moments. So let's look at these forces here. These forces can be divided into two components here because the angle is 45. All of these green components are going to be P divided by square root 2 there. So if I do the force balance in the x direction, this one, and these two will cancel each other, and in the y direction we are going to get RA plus RD will balance this component here and this one right here. So 2 times P divided by square root 2, which is square root 2 P. So this is the first equation we have, and in the second equation we can take moment about this point A. Now for this moment we need to understand that when we are drawing this bone here, these points, point B, point C, and this one right here, they are not following this baseline. So this one right here is at a distance of 13 millimeter in the transverse direction, this is 38, and this one is 20 millimeters. So if I take moment about this point A, I can write down the moment because of these two forces. So P divided by square root 2, which is the vertical component, this will be at a distance of 100 millimeters clockwise movement, minus P divided by square root 2 at a distance of 13 millimeters. So this component, which is the horizontal one, this will give you a counterclockwise movement. Now moving forward, we have this one here. So this is again P divided by square root 2, and the distance in this case is going to be 100 plus 225. So total we have 325 clockwise movement, and this component again about this point is going to give you clockwise, so plus P over square root 2, and distance in this case is going to be 20, and this RD movement about this point is going to be anti-clockwise, so minus RD, and distance from A to D is 450 equals to 0. So solving these equations we get value of RD, which is 0.6788 P, and value of RA, which is 0.7354. So these are the reactions. That was the first part of the problem. The next step is to find out the transverse force and bending moment here. So for that we need to idealize the geometry of the bone first, because these heights are different here. So let's draw a linear approximation of this bone. So if I go here, maybe this section right here is your section AB. So this length right here is 100 mm, and this height here is 13. Right at the middle of the beam, you can see this height is 38. So I can draw another line here. So this one right here is 38. So right middle of the beam, meaning this total is 450. So 450 divided by 2 is 225. So we are going to travel another 125 millimeters here. So after this it comes down and we get somewhere here, and this one is 20. So the next stopover that we are going to have is at 100 from here and 225 here. So this is another 100 mm from here, and the last one we drop down to 0, which is another 125 here. So we can mark these sections as height 1, height 2, height 3, and height 4. So now we can start approximating these functions. So if I look at my h1 as a function of x can be written as, when I reach a distance of 100 millimeters, I should be getting 13. So I can write this as 13 divided by 100 times x. Fairly straightforward. For h2, I am starting with a value of 13. So 13 plus I am covering this gap, which is 38 minus 13, which is 25. Horizontally, I move a distance of 125. So 125. x minus your starting point is 100. So that's how I can write the linear interpolation there. And you can check this. At x equals to 100, we should be getting 13. We are getting that. And x equals to 225, which is this point. So we are substitute 225 here. We get 125, which cancels out. So overall, we get 30. So basically, we are satisfying these two conditions for this linear interpolation. Same manner, I can write your h3x. So for h3x, we are starting with 38. And then we are dropping down to 20. So this gap right here is 18. And this we achieve when we travel for a distance of 100. And in this case, your starting point is this one right here, which is 225. And last one, which is your h4x. h4x can be a starting point this. So we are starting 20 minus, we are dropping by 20, the distance of 125. And your starting point here is this, which is going to be 100 plus 100 plus 125, meaning 325 there. So these are the four height functions that we have got in these four segments. Now for the internal forces for this bone, because your heights are changing, the movements may be changing there. So we can associate one cut at height 1, another cut height 2, cut 3 here, and cut 4 here. Now if you notice the forces on this beam that are given to you, we have one reaction force here, which is Ra, one force P acting right here. This side we have P, we have RD here. At this point we have these two components, P over square root to this side, and similarly P over square root to here. And this point also we have these two forces, P over square root 2 and P over square root 2. Now just to mark these clearly, this is point A, this one is point B, point C, point D, and this one is point E right here. Now that we have defined the geometry of this bone, you can start looking at these individual sections there. So if I look at this cut 1, I'll go and cut this bone somewhere here at a distance of x. So let's draw the free body diagram for cut 1. So free body diagram for cut 1 is going to be with your reaction force Ra here, this force P right here, and unknown your transverse force V1, bending moment MB1. Now for distances, because we are making this cut at a distance of x, so this distance is x, and this height right here is h1. So if I do the force balance here, you can see that your V1 value is going to be minus Ra, and your MB1, because MB1, if I take moment about this point, will balance your Ra x, the distance here is x for Ra, and for this P force we're going to have h1, and it's going to be minus P times h1, because it is in the same sense as MB1. So if I substitute these values of Ra and h1 there, I get the value of V1 equals to minus 0.7354 P, and MB1 equals to 0.61 P times x. So these are the values at section 1. Now when I go to this cut number 2 here, I'll cut somewhere at a distance x in this manner. So in that process I'll cover this part of the beam and this part also, right? So now if I draw the free body diagram for cut 2, we'll have this first part, and then we'll have some part coming from the second segment. In terms of forces, we'll have this reaction Ra here, this force P right here. At this point we have that force coming from the muscle. So these components are P over square root 2, P over square root 2, and at this point we are going to have your unknowns, which are V2 and MB2. In terms of distances, your cut is always made at a distance of x. So from here to here, this distance is x. This height here is h2. This point we had 13 mm. This height here was 13 mm, and this distance is 100 mm from here to here. So now we can write down the moment balance for this and force balance for this. So your force balance gives V2 equals to minus RA plus P over square root 2, and your MB2 in this case will involve all of these four forces. So about this point, your P over square root 2, this one right here and this P, these are going to give you clockwise, this will also give you clockwise, but this force right here will give you anti-clockwise. Now distances are marked there, so if I write MB2, this can be written as RA times X minus P times H2 minus P over square root 2 X minus 100, because if you look at this component right here, it is sitting at a distance of X minus 100 from here, and the last one is going to be P over square root 2 H2 minus 13. So this is for this component, and the distance that we will be looking at is this right here, which is H2 minus 13. So now if I substitute these values, I get V2 equals to minus 0.028 P, and your MB2 comes out as minus 0.03 X plus 63.6 times P. So this is the internal force and moment at section 2. Now in the same manner, we can go to this cut 3. Now for cut 3, it will be easy for us to analyze the right part, and similarly for cut 4, it will be easy for us to analyze the right part in this case also. So if I draw the free body diagram for cut 3, we are going to get one segment here and the other one going in this manner. In terms of forces, we will have RD, P here, those two components from the muscle force, P over square root 2, P over square root 2, and since this is going to be a negative phase, so we are going to mark your transverse force and bending moment in this manner. Now your distance is here. This vertical height at this location is H3. This point had a height of 20 mm. Now this distance from here to here, because your cut is always made at a distance of X, total beam length is 450, so this becomes 450 minus X, and this gap right here, which is this one, is 125 millimeters. So I can write down the force balance for this. So your force balance will give us V3 equals to RD minus P over square root 2, and your MB3 can be written as RD times 450 minus X. I am taking moment about this point, and then you are going to get your P moment, which is at a height of H3 for this one with a negative sign. Then your two forces from the muscle, so H3 minus 20 for the horizontal component and minus P over square root 2, 325 minus X, because about this point this vertical component is sitting at this distance, which is going to be 450 minus 125, so it becomes 325 minus X. So now if I simplify these, your V3 value is exactly same as V2, so 0.028 P, and your MB3 is 0.08 X plus 38.5 whole thing times P. So these are the values at section 3. Now similarly we can draw your section 4. Section 4 will have only the last segment there. In terms of forces, we have RD here, a force P here, your unknown V4 and MB4. In terms of distances, since your cut is at X, this distance from here to here is 450 minus X, and this height here is H4. So now you can see your V4 equals to RD, and your MB4 is equals to RD times 450 minus X minus P times H4. So if I simplify these, I get V4, which is equals to 0.6788p, and your MB4 is equals to 0.52x plus 233, this whole thing times p. So this is the transverse force and moment at section 4. Now we have got all 4 functions for transverse force and moment. Next we can plot these functions. So now I have summarized the value from all 4 sections here, and I have created this axis system for your shear force and your bending moment. Now since we have p appearing in both shear force and bending moment, we can plot Vx divided by p and mbx divided by p. So if I go for the first section, which is between x equals to 0 to 100, the value of your V1 is minus 0.7354. So I can go here and plot it as a constant in this section. Now for your section 2 and section 3, your V2 and V3 same, which is a very small value, but this is negative. So in segment number 2, which is here and here, I can maintain this very small value, which is negative up to here. And the last segment, you can see that this value is 0.6788p, which is on the positive side. It's going to be somewhere here. So I can combine all the boundaries here. So this is the value of your transverse force along the length of the bone with the muscle forces. In terms of values, this is minus 0.74p, this is 0.03p approximately, this is 0.68p. So this is your shear force. Coming for the bending moment, now there are 4 sections. In the first section, we follow this line right here. So for this we need 2 points, one at x equals to 0 and one at x equals to 100, right? So at x equals to 100, the value of this function comes at 60.54p. So I can plot this as straight line here. So this one is 60.54 times p right here. Now in the second segment, we have to plot this line. Now this can be evaluated at x equals to 100 here and x equals to 225 there. X equals to 100, we match the same exact value, but x equals to 225, we get a slightly lower value, which is 56.74. So we get this value right here, which is 56.74p. So I can connect these two with a straight line. So this is how we get your second segment. In the third segment, we have to plot this line. Now this will be evaluated at x equals to 225 and x equals to 325. Now here we match the same value there, but on the right hand side we get slightly higher value, which is 64.85p. So this line goes slightly upwards in this manner. And in the last segment we plot MB4, and for MB4 we need 2 points, 325 and 450. So at 325 we match the same value, and at 450 we drop down to 0 in this manner. So if I highlight the boundaries for this curve, this is the curve that we are getting for bending moment along the length of the bone that is given here with the muscle forces. So I have given you the values there, and if I highlight this area under this curve, this is how your bending moment looks for this particular problem. Now to comment on the compensating effect because of muscle forces, you can notice that if those muscle forces were not there, these moment values were picking up right at the center of the beam if they were following these lines. Because of the muscle force present at this point and this point, we have pulled down the value of moment in this region, which is in the range of 60 to 65p. Otherwise this value would be much higher, right? And if your bone is going through a higher force and moment value for a longer duration, it's not going to be good for your bone health while you are climbing up these stairs.